Oh, yes. If you don't think that I'm excited about the geometric series, then obviously you haven't met me yet. Well, maybe not officially met me, but you've met me through my videos, and you know I get excited about even the smallest math things. This is a huge math moment. So let's get excited. It's going to be awesome and beautiful. Let's dive into the geometric series. So what is a geometric series? When does it converge? When does it diverge? And we can actually find its sum. It's one of those rare series like the telescoping series that we can find the sum of. So the geometric series in general is set up where you have some initial constant times a common, what is known as the common ratio. So R, I'm just going to write that right there, is the common ratio. And I guess that's why I put that equal sign there, right? So I guess we'll put it right there. And then a sub 0, that is just your first term. It's a constant. So it's your first term in the series. So if we expand this thing out, we'll get, well, if I plug in 0, r to the 0 is 1, a sub 0. Then if I plug in 1, I'll get a sub 0, that same first value, r to the 1, plus, then I'd get a sub 0 again, r squared, and so on and so forth, going up by 1 power of that common ratio every single time till you get out to the nth term and keep on going. So that is what a geometric series is. Essentially, you are multiplying by r every time from the preceding term to get to the current term. You're multiplying by r, the common ratio. So when does it converge? I'm just going to give you the straight up down low on this. I guess not the down low, but I'm going to tell you the conditions. We'll prove later all about this, and we'll see why this makes sense with a short explanation right now. But it converges when the absolute value of that common ratio is less than 1. It's that simple. And it diverges when the absolute value of that common ratio is greater than or equal to 1. Why does this make sense? Well, let's think about this. As we go way out to the nth term, right? N's going to infinity. Remember that. So n's going to infinity as we get out there. You're going to be multiplying by r again and again and again. If r is greater than 1, if you're raising a number more than or equal to 1 to the infinite power, you're going to get a number that is not 0. And so that would then diverge, right, by the nth term divergence test. However, if r is less than 1, what you will be doing is repeatedly multiplying by a fraction that is smaller than 1. So what that means is, as we go out to infinity, let's say it's like a sub 0 times some fraction, 1/7. Let's say r was just 1/7. Well, 1/7 to the infinity is 0 because you're taking a seventh of a seventh of a seventh. You're basically cutting a piece of paper, taking a seventh of it, taking a seventh of that, then a seventh of that, until you basically have no paper left. And that goes very, very quickly down to 0. So we end up converging. So we see that as the common ratio, its absolute value is less than 1, then we converge. If it's greater than or equal to 1, we diverge. The other important part in this is that that's all you need to show things are converging or diverging. It's beautiful, isn't it? All right, we'll prove why this is the case in the third video in this chapter. I'm stoked for that. Now, when do we use the geometric series test? Well, anytime you have a common ratio where you're multiplying by the same number each time, or the same value each time to get the next term. So that would be something that looks like this, something that looks like that, and this is just one very specific example with numbers in it, which is kind of nice to see. All right, so let's actually put this thing to the test, shall we? So determine if the series converges or diverges. If it converges, find the sum. I'm going to go over what that sum is, and you know what? I guess I'll put that here as well. And I'll say when it's less than 1 and converges to, and I'm going to give you the formula, and we'll prove this later, and converges to the first term all over 1 minus r. That's only if the absolute value of r is less than 1, it converges to that value. Very simple to calculate. So let me show you this in action. I like to expand this stuff out. I always advise people to do that just to see what it looks like. It is geometric, right? We've got an a term of technically, and I guess it's a sub 1 here. That a term is 1. And then it's r to the n minus 1. You're repeatedly multiplying by 1/2. You'll see it more when we expand it out. So I'll plug in 1. 1/2 to the 0 is 1. Plus 1/2 to the 2 minus 1 is just 1/2. Plus, now we're going to multiply 1/2 by itself twice. 1/2 squared. You're starting to see here that we multiply this by 1/2 to get the next term. Multiply that by 1/2 to get the next term, and so on and so forth. So we'll have 1/2 cubed. And it'll keep going on and on and on until we get out to the n minus first term and then technically continue going. All right, so the question is, does it converge or diverge? Now I'm going to show you the formal justification like always. You need your three parts there: the name of the test, the conditions of the test, and your conclusion. Well, I'm going to say it's a geometric series, so the geoseries, with r, absolute value of r, equal to 1/2. That's the common ratio that you're multiplying by again and again, which is less than 1, so the series converges. You don't have to say a lot to say a lot, so the series converges. The condition of the test was the fact that the common ratio is less than 1. We name the test, it's a geometric series, and we have our conclusion. So what does it converge to? Well, this is going to end up equaling out to the first term, remember, and in that case it's a sub 1, I keep writing a sub 0, all over 1 minus r. What's that going to be? Well, the first term, we saw that when we expanded it out, is 1 all over 1 minus r, and when we simplify that down, that's 1 over 1/2, and this actually ends up equaling to 2. Gnarly. Very, very gnarly, and very, very cool indeed. And you might look at that and be like, that's just equal to 2? What? Let me show you something really neat why this makes sense. Let each of these blocks represent an area, a 1 by 1 block. All right, so 1 by 1 square. That right there is this first term. We'll then show that the rest of the sum fits into this block right here. Well, we take 1/2 of it. There's your 1/2. Then we're going to add on to that 1/4, which is half of that. So there's your 1/4. Then we're going to take half of that half. There's your 1/8. There's your next term, 1/16. And then your next term, 1/30. You starting to see it? No matter how many times we take a half, we're never going to end up filling this up until we get out to infinity. And that's 1 plus 1, which is 2. It's very neat, right? A geometric representation of the geometric series. How about that? Okay, so a couple of key points here. You always want to expand to see the first term. I think it's very important. You don't want to assume the first term is just whatever you see here. You always want to expand it, plug in that index to see what the first term is. Otherwise, we might not always get whatever this term is right here, depending on what this value is up here and what this is. So be careful. Always plug in. If you're asked to find the sum of an infinite series, geoseries may be in the running. Again, it could be telescoping, it could be geometric, and down the road it might be a Taylor series. You'll see that. But for now, geometric series, well, it could be in the running there. All right, let's keep going. We're going to practice just one more of these here. It says, determine if the series converges or diverges. If it converges, find the sum. Okay, now in this case right here, this is A. It looks like a sub 0, and this is r. Now right away we see that the absolute value of this is going to be greater than 1, so it's going to diverge, but let's just stretch it out anyway. That's 3 times negative 1.2 to the 0 is 1. Then we're going to get plus 3 times negative 1.2 to the 1, plus 3 times negative 1.2 to the 2, plus 3 times negative 1.2 to the 3, plus dot, 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 plus 3 times negative 1.2 to the n, and then it keeps on going. So, a couple different ways we could prove that this thing diverges. I'm going to just state this. This geoseries has r equal to negative 1.2, where, and I'm going to write a little bit more, the absolute value of r is equal to the absolute value of negative 1.2, which is greater than 1, or equal to it. So, the series diverges. That's it. So the fact that we have a common ratio greater than or equal to 1, the absolute value of it that is, that means that this thing's going to diverge. And you can also see this from the nth term divergence test. As n goes to infinity, you're going to be multiplying by a number that is far greater than 1. And even if it's equal to 1, your last term's never going to go to 0, so the thing's going to diverge. All right, that's it. I will see you in the next video where we go over how to write repeating decimals in a fraction form with geometric series. Oh boy, can't wait. See you there. Peace.